So, good afternoon, everyone. Shall we start the session? It's past 2. Yeah. So, I'm Nazmul Hasan, and I'll be talking to you today on this color magnitude diagram of clusters, and then we'll discuss how we can make these color magnitude diagram, HR diagram. And so, little before we get into the HR diagram, we'll have a we'll do a little bit of astronomy. And astronomy starts with stars on a clear night. And we all know what stars are. A star is a big ball of gas with fusion going on at its center. Right? So these are huge balls of gas and which are collapsing under its set gravity. And there is a tug of war between the gravity which tries to squeeze the stars and the thermal energy. As it gets compressed, it gets heated up and it tries to swell up, and there is a tug of war between the two. If gravity wins, then it collapses, the cloud collapses to become a star. And if the temperatures are high, which can resist the gravitation collapse, then the cloud will not become a star. So we'll have a look at this in more detail as we proceed ahead. And as we know that stars come in a variety of sizes, they are massive big stars. They are sun-like stars, not very big or not very small, and they are low mass stars. And stars, so the temperature of a star depends on the mass. The larger stars are at a higher temperature, hence they appear to be bluish or whitish, temperature and color related, which we shall see as we proceed. And our sun-like stars, the photosphere, the surface which we see of the sun is the photosphere. It's at about 6,000 Kelvin, and hence we see it as a yellow star. So there's a range of sizes of stars which can have temperatures from 40,000 and down to 3,500. So they come in a variety of sizes and a variety of colors. So what is a star? Basically, it's a nuclear reactor. So as the uh, cloud is collapsing under its self-gravity, the pressure and the temperature at the centers rise tremendously, and when the mass is large enough, then hydrogen atoms get fused to form helium. And if you calculate the mass of, so we require, see, as we know, a hydrogen has one proton and one electron, while helium has two protons, two neutrons, and two electrons. So to convert hydrogen to helium, we would require 4 hydrogen atoms. And as so there are various reactions which go on within stars depending on what the mass of a star is. For the low mass stars, it is the proton-proton chain reaction which goes on. And for higher mass stars, you have the CNO cycle, carbon, nitrogen, oxygen cycle, or you have the triple alpha reactions. And if you look at the mass of 4 hydrogen atoms and you look at the mass of 1 helium atom, you will see that there's a difference in mass. So the 4 hydrogen atoms weigh more than a single helium atom. And the energy, this mass defect which you see, the difference in the mass of what you have of the 4 hydrogen and 1 helium, that gets converted into energy. So you have the famous Einstein's equation of E equal to mc squared, and that is what creates energy at the center. So there's a fusion reaction going on, and it creates tremendous amounts of energy. So trillions of liters of hydrogen gets converted to helium, and the temperatures at the center could be 15 million or, or more, depending on the mass of the star. So if you look at this cloud, these are the kind of cloud. This is a cloud of molecular hydrogen. These are called the giant molecular clouds, and uh, this is the raw material from stars are made. And you can notice that there are small specks on top, small pinkish specks. Those are stars by themselves, and you can see this. The size of a star looks like a speck in this picture, and that could give you an indication of how large these molecular clouds are. These clouds, for them to make stars, we require a few conditions. They need to be dense and they need to be cold. Okay. So by cold, when we say the dense, it means it has about 100,000 atoms per cubic centimeter. And the temperatures can be from in the range of 10 to 20 Kelvin. Mostly these clouds are made up of hydrogen, 75% is hydrogen, and 23 to 25% of helium, and other heavier atoms and other things are constitute less than 2%. Right? So these are giant molecular clouds which compress under gravity to form stars. So there is a genes criteria which is required for a cloud to collapse under its own. There are various processes which can lead to these triggers. So what I was talking about is when a cloud is collapsing under its own gravity. Other than that, there can be a star blowing up, and as it blows up as a supernova, it can drive into these clouds, compress it, and could lead to triggered star formation. Or you can have two galaxies coming and interacting with each other. That's when gas can get compressed, gets funneled towards the center, and stars can start forming. Yeah. So you specifically need some kind of a mechanism to compress these huge clouds, and the G's criteria says that the sizes, the mass of these clouds should be to the order of 10 to the power of 3 to 10 to the power of 5 solar masses, right? And that depends on what kind of temperatures we start off with. So if we are starting off with the temperature of the cloud is say about 10 Kelvin, then you require roughly 10 to the power of 3 solar mass clouds. And if the temperatures are higher, 25 Kelvin or so, by higher, I don't mean very cold, it's 25 Kelvin, which is again pretty cold. You can do with higher mass, you will require higher mass, like 10 to the power of 5 solar masses and so on. So, if a nebula contains enough mass, it begins to collapse under gravity. And when it succeeds in collapsing, depends on the mass and the pressure within the gas and the dust which oppose the collapse. So here you have a low mass cloud, the gravity is low, the pressure inside is high, so the pressure wins and the cloud will not collapse. While in the second cartoon which I have here, you have a high mass cloud and the gravity is large here, pressure is low, and the cloud collapses to form stars. Gravity wins and the cloud contracts. And when star formation takes place, the stars are formed in groups. They are never formed individually, they are formed in clusters. Right? So I've already mentioned that there's a gravitational versus thermal energy battle. If gravity wins, you have star formation taking place, and if the thermal energy is larger, then the cloud does not collapse, but it can and the clouds are of the order of 10 to the power of 3 to 10 to the power of 5 solar masses. And these radii of these clouds run into light years. They are huge clouds. And as it starts collapsing and the density starts increasing, then uh, it forms fragments in it, and these fragments form different stars. So you can see uh, protostars being formed here. There's a big cloud which collapses. Within that, fragments are formed, and these cloud fragments further collapse to form masses sufficiently. Then the thermonuclear reactions begin, and so on. So stars are born in groups. They are never born in isolation. They are always born in groups. And a field starts up from clusters. So if you look at our sun appears to be a lone star. It doesn't seem to have any companion, no siblings with it. But surely our sun must have been born in a cluster, and then it got ejected out. So as these clouds, the stars are formed in clusters, they interact with it gravitationally, and there's these two-body, three-body interactions, and the central core starts compressing further, and some of the stars can be ejected out. And then there are other processes too, which can lead to evaporation of these star clusters or disruption of star clusters. So we shall not be discussing that in this talk. So a star cluster is a sample of stars formed from the same molecular cloud, where all the stars have the same age, same chemical composition, and at the same distance from us. They only differ in their masses. Because when this collapse takes place, the cloud itself can be of the kind where it is denser in certain parts and less denser outside. So stars formed, they can be of a variety of masses, more massive. But since they are being formed at the same time, that's why we say the age is the same, and it's the same raw material from which the cluster is being formed. So the chemical composition is essentially the same. And the distance to these stars compared from us, from we as observers, it's about the same, right? The star clusters also extend over a large distance, but compared to the distance which our distance to the cluster is, that is pretty negligible. So from the observer's point of view, from our point of view, they all appear to be approximately at the same distance. Obviously, some will be on one side of the cluster closer to us and some on the other. But if you look at the radius of the cluster and the distance from us to that, it's not too much, and hence they are essentially at the same distance from us. So these clusters, they come in essentially two types, and we also have associations. We have open clusters and globular clusters. There are two pictures here. The one reddish one on the right hand side is a picture of a globular cluster, which looks like a globule. It looks like this very beautifully spherically distributed set of stars, while the other one, on the one below, is an open cluster, and the name itself suggests that these stars don't seem to be so closely packed, and these appear to be spread out and open. And then we have the associations. What are globular clusters? Globular clusters are mostly found in our galaxy, in our Milky Way galaxy, in the halo, where you have these clumps of stars, the halo of a galaxy, and they appear to be compact. The number of stars in globulars can range from 50,000 to a million, yeah, order of magnitude of tens of thousands to millions of stars. The masses of these globular clusters about 10 to the power of 5 solar masses. Color is mostly red, indicating that these are old stars or low mass stars, and we will see why it is so. And the age of these stars, yeah, they are very old stars, about 10 giga years or so, 10 to the power of 10 years. Distribution is mostly broadly distributed and are gravitationally bound, and these globular clusters are spherical in shape. These are population 2 stars, and the orbits of the stars in these globular clusters is highly eccentric or elliptical. They are all going around the center of these, right? So these are basically stars which have formed a long time back, and they have uh, relaxed into a globular structure, right? While the open clusters are found in the disk of our Milky Way. So, as you know, the structure of a Milky Way galaxy, it essentially has a disk which is rich in gas. It has a bulge, the central bulge, and it has a halo. So, the basic material from which stars are formed is gas, and the gas is present in the disk. Hence, the star formation in our galaxy and in all uh, spiral galaxies is happening in the disk, while the halo is devoid of gas, or even if there is gas, it is diffuse. It's in a state of diffuse. While in the disk, you are having it in a in and star formation is taking place. And what you see here are all kinds of stars in the disk of a galaxy: young stars, old stars, massive stars, low mass stars, and everything. Right? So in globulars, you don't have much of gas, and hence you don't observe much of star formation. In fact, in earlier times, we thought that star formation is absolutely stopped in these globulars. So what we see is open clusters are, the appearance is loose. They are not as compact as the globulars. The number of stars can be in tens, 20, 50, and so on, up to thousands of stars. And the masses of these clusters are about 10 to the power of 5 solar masses. And the color is mostly blue, indicating these are massive stars, and hence you have the blue color. The age ranges from 10 to the power of 6 to 10 to the power of 8 years, and the distribution of these clusters, like I mentioned, is on the plane of the Milky Way, right? These are population 1 stars, and the orbits are regular. So these clusters, these star clusters, go around in almost circular or elliptical orbits. They go around the center of our Milky Way in a disk, right? While in globulars, you have all kinds of tumbling orbits. A good example of an open cluster is the Pleiades cluster. You have these, it's in the Taurus constellation and popularly known as the Seven Sisters. But if you observe through a telescope, you will see stars many more than these seven. But to naked eye, you see only seven of them, and this is what it is. Yeah. So the processes. Yeah. So what is essentially happening in a star is you have the gravitational gravity which is trying to squeeze the cloud into a star, and as it squeezes, the temperatures start rising up, and this tries to blow up this star, right? The cloud. So initially, there is a tug of war between that, and the whole system oscillates, and the stars pulsate. So gravity wins, it contracts, and the surface area becomes lesser. So the area from where it is emitting light gets reduced. Yeah, so the brightness of a star, as we shall see as we proceed ahead, depends on the temperature and the radius of the object, right? There are two things. So if the temperature is high, the star is bright, and the temperature, if it's low, then you have a fainter star, right? So one important thing is the temperature of the star, and the second thing is the size of the star. You may have a star which is not very hot, but if it's a big star, then it will which it's emitting light is pretty large. So initially what happens is the stars, before they come and sit on the main sequence, which you see in this diagram here, we'll have a look at it a bit more carefully later. This is called the main sequence. The diagram which we see here is very important for what we are doing today. What we have is the temperature on the x-axis in the reverse order, and you have the absolute magnitude on the y scale. This is called the HR diagram. HR diagram, Hertzsprung-Russell diagram. Okay, and what you see on the x-axis is this O indicates O-type star. This is a spectral type of star, and it was later realized that the spectral type depends on the temperature. So O stars, B stars, A, F, G, K, M. These are the different spectral types of stars. And there's a mnemonic with which you can remember this, which says, "Oh, be a fine girl, kiss me." That's how earlier it was used, but now people have come up with many others because it was a bit improper for women. You know, why girl kiss me and all that. So this has changed now, but O, B, A, F, G, K, M. O stars are hot stars, while M are the relatively cooler stars. And what you see on the y-axis is the visual absolute magnitude. And if you plot this diagram for most stars, you will see that many stars sit on this line, which is called the main sequence. This is the time when stars are converting basically hydrogen to helium. That is the process going on. And after that, it wanders off from that and it goes into the giant stage and so on. Okay. But before it sits on the main sequence too, you have certain Hayashi and Hene tracks, which you shall see as we proceed ahead. And what happens is the stars, they go through a system of collapse. So as it's collapsing, the radius is decreasing. And you see, let me see if I can annotate spotlight. Yeah, oops. Yeah. So anyway, I'm unable to do that here. Okay. Yeah, I'll see if I can draw on this. Yeah, so as it's shrinking, you will see that they come like that, then they move, and they finally come and sit here, right? So as this kind of a motion indicates that their magnitude, the visual magnitude is decreasing, which indicate it is collapsing, right? So the luminosity is decreasing, the size is becoming smaller. And as this happens, the temperatures at the center becomes high, the gravity becomes high, and there's a greater amount of nuclear reaction which goes on, and it gets hot. And as it gets hot, it starts swelling up again. So the stars, they become they become brighter and they move up. And as it goes up, the star is swollen up, so the reaction at the center comes down, and hence gravity starts bidding on it, right? So this kind of a pulsation goes on till the time the star comes and sits on the main sequence. So depending on what the initial mass of the star is, they come and sit on the main sequence. And they sit here for different amounts of time. Low mass stars sit here for about 10 to the power of 10 years, while the high mass stars in a few million years they go off. Right. So basically what's happening is, as the nuclear reactions begin, hydrogen starts getting converted to helium, and it continues to do so. And when it reaches the stage when the whole of hydrogen is converted to helium, so there's no more reaction which just goes on, and hence the reaction stops and it starts getting cooler. So the star starts collapsing, right? So there's no thermal pressure and it starts collapsing. And as it collapses, uh, the unburnt hydrogen in the outer shell gets fused, and some of the helium also fuses, and there's a sudden burst of nuclear reaction which goes up, and there's a tremendous energy created, and the star starts becoming big, and it becomes big to becomes a giant. So it goes up and becomes a giant star. Okay, and it lives here for a while, throws out its outer covers, and then it shrinks to come and become a dwarf star, which will come and sit here. Yeah. Yeah. So yeah. So first it's hydrogen getting converted to helium. Then the helium, if the mass of the star is massive enough, then helium fuses to form carbon, and carbon can later converts to oxygen, and so on, and the whole process goes on till it reaches the stage where you have iron at the core. So the stars which are not very massive, they only convert hydrogen to helium and stop as helium dwarf stars. Those who are a bit more massive, they go further and create carbon as well. And more massive, they create magnesium, oxygen, and so on up to iron. After iron, it becomes an exothermic reaction. It requires more energy. So the other elements which you find on the periodic table cannot be created within the center of stars, but they are created when massive stars they explode, right? So just a minute, I'll have to. Yeah. So what we see here is the mass is the key driver for stellar evolution. Low mass stars have a main sequence life of about 10 to the power of 6 years, while the high mass stars, high mass stars have lower lifetimes. They have about million years, while low mass stars like 0.5 solar mass stars, they live for giga years. Yeah. So okay, so from here I will hand over to Priya, madam.
Hello, yeah. So I am back. Sorry, but I do think you all must have enjoyed the refreshing change instead of seeing the same person every day. It's nice to to hear someone. Right? So thanks for helping, and I'll continue with what we did. So you'll have already seen what are star clusters. And now we're going to come to basically the topic of today, which is plotting of what is called the HR diagram, which is called the Hertzsprung-Russell diagram. And that is one of the most important diagrams in astronomy. And it is the basis for a lot of understanding of astronomy is based on the HR diagram and what we know about. So now what's the basic problem? Let us see what's the basic problem. So if you look over here you have a mosquito and you have a bunch of people over here. And let's try and think of how would it be for this mosquito if the mosquito wants to decipher what a human life is all about, right? So that's the kind of problem we actually face with stars. And instead what we face is something even worse. We'll just see that. So for example, if you actually see a human mosquito, a male mosquito lives for about 10 days, female one for 42 days, 50 days. So human life is about 3,000 mosquito lives, right? And so in short, you would have a whole chain of 3,000 mosquitoes who will have to describe to, would have to describe to one another to know how is a star born and how does it die, right? Sorry, for a human being. But if you do it with stars, you'll see that stars are generally of 1,000,000 years or 1,000,000,000 years, right? So even if you take human lifetime to be 100 years, right, a star life is going to be at least 1,000,000 times or 1,000,000,000 times more than a human life. And therefore, we do not have the luxury of actually sitting back and watching and try to understand how is a star born, how does it live, how does it die, etc. Right? And therefore, what we are going to do is we actually have to use the laws of physics to understand how are stars born and die, right? So the basic problem is, like I said, it's a difference in the age, lifetime of the mosquito and lifetime of a star, or similarly like it in our case. So yeah. So what is the thing? How can the mosquito solve the problem? So the mosquito can actually observe people, look at a whole bunch of people, and try to actually characterize these people, right? So you can see the hair, weight, hair color, height, weight, etc. And try to see what are the properties. And then this mosquito has to then figure out how do these main properties define a human life cycle, right? The height, weight, age, etc. And how do they assess? What should they notice in people when they want to assess, for example, the age of people, right? So, 1 minute. So this is comparable to that problem. Oops, sorry. I'm sorry, but my slide is not moving. I'm trying to make it move. It's somehow refusing to move. I'll do a stop share and I'll share again. I'm sorry. Okay, yeah. So let us see, if you look at human beings, what would be a human HR diagram? If you were to draw an HR diagram for human beings, what would we see? So the crucial parameters in human beings, when you look at this person over here, what you notice is their height and weight, right? And that is essentially the keys which tell you things about the person. So if we were to plot a height weight plot for human beings, we would get something like this. So you'd see that there are some human beings, lesser number of human beings, which have a lesser height and a lesser weight. And then the bulk of human beings are all over here, which have a weight ranging, say, from 50 kilos to 80 kilos, and a height somewhere between this, right? 1.5 meters, less than 2 meters. That's the kind of height. And you'll see that they are lesser over here and more over here. So these are the children. So we know that because you have more points over here, so stars or human beings spend more lifetime in this period, right, which we call adulthood. So most human beings who are more than 20 years old up to whatever 60, 80, 100, all of them will occupy this part of this plot, but only the less than 20 or less than 15 will occupy this. And that's a smaller fraction of the human lifetime. So what you can see is that by the population, when you see that there are lesser points at this point, you can see that that's because of this reason, right? Because lesser time of human lifetime is spent in this region with a lesser height and a lesser weight. right? And this is going to be something important which we'll also use when we try to look at stars, right? Looking at the population, how many are there? If we want to study stars, what we use is something called the Russell-Watt theorem. And the Russell-Watt theorem states that for a star, the most important components are its mass and its chemical composition. And exactly this is what gets translated into the HR diagram, which we are talking about today, where we have the luminosity versus the temperature, right? So this is Hertzsprung and this is Russell. And they plotted this diagram where you had the y-axis with luminosity and the x-axis with temperature. And you can see where are the stars located in the HR diagram, what happens when stars evolve in the HR diagram, and we'll also see what does the HR diagram of a star cluster tell us. So the HR diagram, like I mentioned, is a tool we use to study stars, and it plots these two quantities, and we'll see how does that related. Now, luminosity, we already spoke about it on the first day. Luminosity by Stephen Boltzmann's law, the flux is nothing but sigma into T power 4, right? Where sigma is the Stephen Boltzmann's constant and T is the temperature, and this is the flux. Now, the total area of the star, since it's a sphere, it is 4 pi r squared, right? And therefore, I can get the luminosity. To get the temperature, we will see how do we get the temperature of stars, assuming that stars are blackbody radiators. So how do we get the temperature of stars? You know that when you put white light through a prism, it splits into its colors, right? And these colors have different wavelengths, which are shown on this electromagnetic spectrum over here. This is the small range of visible light, but there are a whole amount of electromagnetic spectrum, which is X-rays and gamma rays. These are shorter wavelengths, higher frequencies, and microwaves and radio waves and infrared, which are longer wavelengths, shorter frequencies. So what happens is, if you had a black body, some of you all may have studied Planck's black body radiation. So you know that a black body radiates somewhat like this. And therefore, supposing I could sample the radiation of this object at say 3 points, 1, 2, 3. I can fit this to a black body curve so that I can find out the temperature, right? You can see that this first curve is for an object at 12,000 degrees, second one for 6,000, third one for 3,000. So if you look at the sun, the spectrum of the sun is the black curve. If I plot it, you can see that these peaks coming, these are what are called emission lines. If I fit this curve, I'll get this magenta curve, which gives me the temperature of the photosphere of the sun, which is 5,800 degrees Kelvin. And then in this, I have these emission lines, which come up over here, right? So if I want to measure temperature, I basically look at the spectrum or the spectral class of stars. If you had a hot body with a cold amount gas in it, you would get what is called absorption spectrum. If you had a hot body with hot gas over here, you will get a emission line spectrum, right? So that's what we actually look for. Now, how do we actually measure this spectrum? We measure this spectrum by actually using what are called bolometric magnitudes. So the flux of the object, we measure it with respect to a wavelength. How do we do that? We actually have what is called photometric systems, right? So what do we do in photometric systems? We have filters. If you remember, we spoke about filters the other day. When we took our data, we took it in 2 different filters, right? Then we did it yesterday for the images, 814 and 555. So here you can see that you have these 2 filters and narrowband filters. So what are filters? They are something like this. They will only allow light which has a certain wavelength. This is the central wavelength. So the U-band filter has a central wavelength at 3,600. The B-band filter has a wavelength 4,400, and the V-band filter has a center at 5,500, right? And what you can see is the only light coming within this filter will be permitted to come to pass through the CCD, for example. If you remember yesterday when I showed you CCD and astronomical images, we saw filters also. So here we have these filters. If we take the difference in brightness in 2 filters, okay, that is what we call a color. So there is a B filter, which is over here, the B filter, which has a central wavelength of 4,400, a V filter with 5,500. And if I take the brightness of the star B minus V, we call that color. So this is the magnitude in B minus the magnitude in B, which gives me that, right? So magnitude is the brightness scale which we use in astronomy. Now, when we plot the HR diagram, now we saw how do you find luminosity and how do you find temperature. So if we actually plot luminosity versus temperature, and we plotted for stars of different masses. In a minute, I'll talk to you about masses. How do we get masses of stars? You see that these stars actually take almost a straight line, right? And this straight line, it's not exactly a straight line, but they come along this. And this is what is called the main sequence. So most stars lie along this line on this HR diagram, and they are called the main sequence stars. So here is an HR diagram which is plotted using data from the Hipparchus catalog satellite. So there was a satellite sent which is called Hipparchus, and using that we had measured the brightness of 1,000,000 stars, and with that we actually got this, right? So the HR diagram, the good part, the important part of the HR diagram is that it is used to find out all parameters of the stars, and that's why the HR diagram is so important. So if you can plot a star on the HR diagram, which we will be doing today, you can get all parameters for that star, which include the mass, the radius, the temperature, and its age. You will get all those parameters from the HR diagram, and that's why the HR diagram is so very important. So typically in the lifetime of a star, most of the time the star sits over here, which is called the main sequence. So the main sequence is something like adulthood, right? We spend most of our time in this region, which is the main sequence. After the star finishes the main sequence and it starts evolving, it moves to this region, which is called the red giant region or the supergiant region, okay, where the star basically swells up and becomes a giant, because of which it becomes very bright, right? And then gradually the outer shell is lost and you only have the core left, and that is the white dwarf stage. So the main sequence, then you move to the right, and then you come to the left. Remember in astronomy, hot things are on the left over here, cold things are over here. So giants are cold stars, they are big and cold stars, while white dwarfs are small in size and they are hot stars. So typically, if I were to look at radius on the HR diagram, this is the HR diagram, you can see that radius increases like this. So these are the giant stars which have large radii. For example, the radius is 100 times the radius of the sun over here. While the dwarfs, which are over here, you can see these have a radius which is 1,000 times the radius of the sun, right? And so what you can see is now we already have an idea of the sizes of stars, right? And based on the sizes of stars, we also classify stars into what are called luminosity classes. So obviously you can see that these stars are the brightest stars, which are up over here. So supergiants, giants are the brightest stars, which are sitting over here. White dwarfs are faint, and main sequence stars have a whole range of brightness, right? So therefore you can actually use these luminosity classes also to classify stars to know what is their brightness. And therefore we actually can define families of stars. So we have the main sequence, you have giants and you have supergiants. These are the red dwarfs, and here are the white dwarfs. Keep this in mind because we'll be using that in a minute. So here's an HR diagram if you want to plot the HR diagram. The one problem is, how do you get the mass of stars? So the mass of stars can be only found if stars are in a binary system, right? So typically if stars are in a binary system, you have this red star and the blue star, they will go around each other around the center of mass, right? And using their time periods, like we did in the exoplanet exercise, using their time periods, we can actually get the masses of these stars, right? So let's say now we get the masses of stars. So if I know the mass of stars and I plot them on the luminosity versus mass diagram, okay, we are looking at the mass luminosity diagram. This is luminosity and this is mass. You can see that as the mass of the star increases, obviously the luminosity of the star also increases, right? So you can see that the main sequence is actually a mass sequence, okay? In the sense, we'll look at it in a minute, that these are the stars which are more massive. These stars have a lower mass, right? So this is a mass sequence, the main sequence, where mass goes this way and high mass is here, low mass is here. So radius, large radius is here, small radius is here, large mass is here, and small mass is here. So this is exactly what I was talking about. If in the HR diagram, you plot luminosity versus temperature, this size is large radius, small radius, this is large mass and small mass, right? So that gives us the HR diagram. So stars in the upper right are large, stars in the lower left are small, and stars in the, if you look over here, on the lower, on the left upper left are massive, and lower right are low mass, right? So these are our HR diagrams. Like I told you, it's very important because if you can plot a star on the HR diagram, you can get all the parameters for these stars. You'll get the radius, you'll get the mass, you'll get all that. So now we'll come to the part is how do we get the age of these stars? So if you were to look at a star cluster, right, you will get something like this, okay? Because in the star cluster, they are all born from the same molecular cloud. So all of them have the same chemical composition, the same age, only all of them have different masses, right? And so I had explained to you that the high mass stars, they evolve faster than the low mass stars, right? And therefore, if you look at this over here, you can see over here that if I have a cluster over here, these upper high mass stars, they start evolving faster, they move towards the right hand side, and gradually these stars which have the next masses, they will move to the right hand side, right? And then they'll come over here and become the white dwarfs. So you can see this in this animation over here. Here's a star cluster. You can see the age over here. So this is, as it's getting older, there are more stars over here. There's less on the main sequence and there's more over here. So I'll repeat this thing. You can see it once again. I will repeat it. You can see that this is how it's evolving, right? So typically, let's go back to our globular cluster. Typically, you can see in globular clusters, you see the age is 10 million years or 10 power 15 years. Most of the stars have moved over here and they've come over here. So you don't have many on the main sequence, right? So typically a globular cluster, like what we are going to plot today for our globular cluster, which we had yesterday, you will see that most of these main sequence stars have moved to the right. They've become giants, and lesser stars over here at the main sequence. You may have some white dwarfs, but then you'll have these things, and you'll have these interesting stars, which are called the horizontal branch stars, right? Now, these horizontal branch stars, they are these stars over here, the yellow stars, which you can see. And one thing which you can notice in this plot is that these horizontal branch stars have almost a constant brightness. Their brightness is a constant, right? This is flat. The horizontal branch stars are flat over here, right? These ones. It's almost flat. Little bit of a turn, but not much, right? So that's why it's called the horizontal branch. Now we'll come to a very important concept in astronomy, which is called absolute magnitude. Now you know that when the brightness of the star is measured, it's measured in what is called the apparent magnitude, right? So the apparent magnitude is the brightness of the star when you observe it, right? But we know that these stars are going to be at different distances towards us, right? So the closer stars are obviously going to look brighter, and the further stars are going to look fainter. So for example, if you had this star and this star, let's say both of them are at the same brightness, right? But at different distances. So this guy, because this one is further away, it's going to look fainter to you. But this star, because it's closer to you, it's going to look brighter. Now, therefore, in astronomy, to define the brightness of stars, we have a scale which is called absolute magnitude. So for absolute magnitude, we put all stars at the same distance, which is the distance of 10 parsecs. So I get this further star at 10 parsecs, I get this one at 10 parsecs, and then I measure its brightness. And that is what we call absolute magnitude. And therefore, if small m is the apparent magnitude of a star and capital M is the absolute magnitude of a star, we have this very important formula, which is m minus m. We also call that the distance modulus is equal to -5 plus 5 log d. So obviously you can see that if I put 10 over here, if d is equal to 10, right, then log d is equal to 1. So this will become +5, this will be -5. So m minus m will be equal to 0, right? That means the apparent magnitude of a star will be equal to its absolute magnitude, right? Now, I wanted to show you this. If you move to absolute scales, many of you all may be familiar with this constellation. This is called the Canis Major, which has the next brightest star in our sky after the sun. The next brightest star is called Sirius. Okay, so you have 1, 2, 3, 4, 5. This is called Canis Major or Sirius. You can see it in the skies even nowadays. If you look up early in the evening, you'll see it before 8 o'clock, 7 o'clock, you'll see it up in the sky. It's a very bright star. This is how it looks in apparent magnitudes. In apparent magnitude, Sirius is the brightest star, right? I told you after sun, it's the brightest star in our sky. But if I were to convert this to absolute magnitudes, you will see that these stars would look like this. So actually this star will actually be the brightest in Canis Major, this one, the tail. This is actually Canis Major, which means a dog. So this is the tail. This star is the brightest, not Sirius in absolute magnitudes, right? So why is this interesting? Because like I told you, the absolute magnitude of these horizontal branch stars is fixed, right? And if we know the absolute magnitude and we know the apparent magnitude, we can do apparent minus absolute to give us the distance modulus. Once you have the distance modulus, you can get the distance to this cluster or the star if you know this thing. And that's exactly what we are going to do today, right? So what we are going to do is we are going to plot the color magnitude diagram of the globular cluster we were looking at yesterday, and we will find the horizontal branch stars, and we will use that to find the distance of this cluster. So I'll stop sharing this thing, and I'll give you this assignment later. But let's go back to TopCat, right? So does everybody have the file? I'm going to open TopCat, right? I'll share my screen. I hope you can see TopCat here. Yes. And what I'm going to do is I'm going to share with you all on the chat both the files which we got yesterday. Okay. Both the output files I will share with you. Okay. And this is on my Day2. Right. So I'm going to share two files with you. One is the G photometry file, the G band photometry file, and the other one is the R band. Some of you all did had problems in running APT tool yesterday, and therefore I'm sharing these two files so that in case you had a problem with accessing on any of these two files, you can access it from here, right? So I hope most of you all can get access to these files. I will mail them also to you all, but you can have a look at them, okay? So let's open TopCat, right? And in TopCat, I am going to open this file. Actually, what I will do is, okay, you can say file and you say load table. Now open the first file I sent you. So the first file I sent you was called ngc5466 gfort. Is in table format over here. Select, okay, and say okay. Now you can click on this table and look at the file. I hope everybody is managing this. I'm going to pause for a little bit so that if somebody has not managed this, please write on the chat window if you did not manage to open the file with TopCat. Yeah, please let me know. I'm waiting for your response to know whether you managed to open the file. Please write yes in case you managed to open the file, then I can proceed, right? So I'm just pausing for a minute, and please let me know if you managed to open the file. Yeah, please write yes if you managed to open the file. Yes, okay, very good. So let's open the second file. I'm closing this thing. Let's open the second file. So you say file, load table, and open the second file I sent you, which is ngc5466R. Okay, this is the R band file. Select table format CSV and say okay. So there are two files. One is the GFORT and one is the RFORT. So these are the results of what we did yesterday. For those who were not present yesterday we used a cluster which is 5466. It's a globular cluster, and we created a catalog of the stars of that cluster. Okay, so these two files were the output of what we did yesterday, right? Now I can plot these two files and show it to you. This is the plain plot in TopCat, and I can show you the G band photometry. Put the X as RA and put the Y as DEC. So this is G, and hence I'm going to make this color green, right? And I will add the next file, which is the red file. So I'm going to add the second photometry, which is the R fort, and the R fort I will put it in red color, right? And I'm going to make it red, right? Now these stars are almost one on each other. Right. And therefore, you, if you want to see both of them, this is green and this is red. So I'm going to make it a little bit better visible. I'm going to slightly change the size of the green. So I'm going to make green as a box, which is a little bigger box, 3. And sorry, I've made red a little bigger box. This is not red. I'll change the color. Let it make more red. This is pink. I'm making it red. So what you can see is the red stars are there and the green ones are inside, right? So I can zoom this also and show you that you have, one is the star from the green catalog, the G catalog, and the red square is the star from the red catalog. Now, if we want to match these, we can match this very easily. In TopCat, look at these matchsticks. Can you see matchsticks over here? So the matchsticks can be used to actually match two catalogs. So both these catalogs have the RA and DEC for each of the stars, right? So what it has to do is look for a star in the G band catalog with the RA and DEC, find the same star in the second catalog in the R band catalog and match them. So please click on these two matchsticks, okay? Click on the matchsticks. Here we have sky. It's looking for, within the sky, it's going to search. This is the first one, which I'm going to put over here, which is G-FOT CSV. RA column, it's going to ask you, what is the RA column? So you say the RA column is aperture RA. DEC column is aperture DEC. The second file will be the one, the R band one, which is this one. And here I'm going to take this one to be aperture RA, and I can take aperture DEC. So now what am I going to do? I am matching these two catalogs, okay? One is from G band and one is from R band. I'm matching both these catalogs to match these two stars. So I can say go. If you remember, we had 2,388 stars. But you can see that not everything gets matched. There are 4 stars which did not get matched. And that's possibly because these stars, they were slightly shifted, right? So maybe 4 stars did not come in the same field, but otherwise 2384 got matched. So I will say okay. And now this is my matched file. So what you can see in this matched file is, here you can look at this table. You can see the first file all has _1. So this is all for G band. So for G band, this is the RA, this is the DEC, right? Here, if you look, this is the magnitude, this is the G band magnitude. If I want, I can right click this and I can rename it as G. Okay, I can name it as G. This is the G band magnitude. This is the errors in G band. And then here, when I come here, I can move this ahead and you can see I'm now, this is the image, etc., the details. And now this is the second one. The second one, so this is the R band catalog. This is the RA, this is the DEC, and here is the magnitude or the brightness. So this magnitude 2, I can replace column and I call it R. Okay, fine. Now I am going to make an HR diagram for NGC 5466 because I have the magnitudes in 2 bands. I have the magnitude in G band and I have the magnitude in R band. So I'm going to again click this thing. I'm going to close this match window. I'm going to click this thing, which is for plotting. And here when I plot it, I will choose this file, which is match 2425. And here on my x-axis, if you remember, I called mag1. If you have still mag1, it will be mag1. Otherwise, I called it G. And the second one is R. If you remember, I called it R. It may be mag_2 for you. And here I can call this G. Right? So I cleverly renamed it so that it becomes easier for me to do. And I say enter. So this is the HR diagram. The only difference is that in astronomy, we actually do it in the reverse scale. So we flip this. So this is brighter. The magnitude scale, you know, is a reversed scale. So this is brighter, this is fainter, and this left is hotter, this is colder, right? So if you remember the HR diagram, let us look at it more in detail now. I'm going to make this a little, I will adjust the range. So I can click on range and let me make my range say -1 till, for example, 2, right? And the y-axis is fine. So this is my thing. But you can see that this is where the main sequence must have been. And these stars have turned away. This is called the turn off, and they've become giants, right? These stars have become giants because this cluster, it's a globular cluster and it's quite old. So therefore, most of the main sequence stars now have become giants in this. They are not on the main sequence. So this is the region. If you remember the old HR diagram plot, this is the, I can show that to you also. I will show that to you. So let us look over here. You see, this is the HR diagram I showed you for a globular cluster. So you see there are very few stars here on the main sequence. There are lots of stars over here, which are the giants. And there are these, which are the horizontal branch stars, right? This is what the HR diagram looks like for a globular cluster, right? So now what I'm going to do is I am going to reduce this, and we will, I will look at, we'll get back to TopCat. So here is the HR diagram we have plotted, right? So that was the purpose of today's exercise, to plot this HR diagram. Now, like I told you, if for this HR diagram, I want to derive, say, the masses of the stars, right? Or the radius of the stars, I have to do that by finding out the distance to the star. Because the most important parameter for me to know for a star is the distance to it. Because I know that because of the difference in distance, a star is going to look fainter or brighter, and I will not know the correct brightness of the star. So now how do I do that for this? Now here is the horizontal branch. If you remember, I told you that the horizontal branch is almost flat, right? That means it corresponds only to a certain brightness. So what I can do in TopCat is I can click on subsets. Please click on subsets and click on draw blob subset. So what I'm going to do is I'm going to identify all the horizontal branch stars, and I'm going to find out their average brightness. So I will draw blob subset, and this is the horizontal branch stars. So I'm marking them over here. And then you go back to subsets, you say finish drawing blob. Okay. And we'll call these horizontal branch stars. Okay. So I'll say add subset horizontal branch. Okay. And then we go back to our TopCat window. In TopCat, if you see, there is something called this sigma. This sigma basically gives you stats. It gives you statistics for different samples. So we'll click on stats. And here you can see subset for calculation is all. Instead, we will choose HB. HB is the horizontal branch stars. So if you click on horizontal branch stars, look over here, you will see that we'll see what is the G magnitude. You'll see it is 16.54. I hope you all have managed this, or should I repeat this step? Should I repeat this step? So we have, what we have derived is we've got the horizontal branch brightness. I'll repeat. Okay, I'll repeat it. Let's close this. I'll do it again. I hope you all have your HR diagram, right? Everybody has the HR diagram. I hope everybody has the HR diagram and you've plotted this. Please write yes. Yes, everybody has the HR diagram. Now I told you is on this HR diagram, you identify the different stars. These stars are giants. These stars, right? These are the horizontal branch stars. And like I told you, the horizontal branch stars have a fixed magnitude, absolute magnitude. Now here what we are looking at is the apparent magnitude, right? This is the apparent magnitude. So what happens is, like I told you, if I want the distance to stars, I need the difference between apparent magnitude and absolute magnitude. Now the absolute magnitude of horizontal branch stars is 0.6. Okay, it is 0.6 is the horizontal branch stars absolute magnitude. But you can look that in this cluster, it's actually not lying at 0.6. It has some other apparent magnitude. So I'm trying to find out the average apparent magnitude. So I can even just put my cursor over here and you look down, you can see 16.52. So if you want, you can just take an average central point over here And you can see that horizontal branch stars have a brightness of 16.52, right? You can do this. Or the other step I showed you was that you can click on subsets and click on draw blob subset. So we will actually try to find out the average brightness of a horizontal branch star. So I will say draw blob subset. And then I will mark this region. Okay? Use your mouse, use your cursor to mark this. After you mark it, you again click on subsets and you click on finish drawing blob, right? Finish drawing blob. And here you can write horizontal branch. You can write horizontal branch. Okay, and this is my subset. So therefore you can see these green stars over here are the horizontal branch stars. Now what is their average magnitude? How can I find that out? I go back to my TopCat screen and I use this thing, which is the stats. This is to find out stats for stars. So I'll click on this, right? And here I can see the G magnitude. You can see the G magnitude. This is the G magnitude for the horizontal branch stars. And you can see it's 16.53. Okay? It's 16.53. Now what I'm going to do is I am going to use this information to find out the distance to this cluster. Like I told you, for G magnitude, the absolute magnitude for horizontal branch stars is 0.6. Okay? And we found our apparent magnitude to be 16.52, right? So we got 16.52, right? So I can find out my M minus M. So what is M minus M? Apparent magnitude is 16.52 and my absolute magnitude is minus 0.6, right? So I'm going to do 16.52 minus 0.6 and I call that the distance modulus. I substitute it in this formula and I find out the distance to this globular cluster. How will I find that out? I will find that out like this. I will, let me open my calculator. Here's my calculator. So what do I have? I have 16.52 minus 0.6. This is my distance modulus, right? Which is 15.92. And if you remember, I told you that this 15.92 is nothing but 5 log D, right? Minus 5, right? So therefore what I do is I will add 5 to this, right? So I will add 5 to this, correct? I will divide this again by 5 because I have 5 log D. So I'll get divide by 5. I get this 4.184 and I have now got to take anti-log of 4.184. So therefore that's what I will do. I will take 10 power 4.184, right? I will say equal to, and this is the distance to this globular cluster. So this globular cluster is a distance of 15,275 parsecs. If you want to verify that, we can do that over here. Our globular cluster is NGC 5466, and I can say 5466 distance, right? This is the distance in light years. Let me write the distance in parsecs, because our answer is in parsecs. So I get this, and you can see that it is at a distance of here. You can see this answer over here, the distance of 5466. This is what we were studying since yesterday, the globular cluster. You can see 5466, our globular cluster, is at a distance of 15,912. Right? But we got an answer 15,275. This is the globular cluster, and we got a distance of 15,275 parsecs, right? So that is the distance which we have derived. So what I showed you today is how can you actually derive what we saw today was what was the importance of actually if you remember when we use this calibration, we use this to get the distance to the cluster, right? So essentially, how did we do it? Because we plotted the HR diagram of that cluster, right? So the most important thing is, first of all, you need to plot the HR diagram of the cluster. And once you have plotted the HR diagram of the cluster, specifically, open clusters will not have horizontal branch stars, but globular clusters will have horizontal branch stars, and you can use that to actually get the distance to a globular cluster. If you want to get the distance to a open cluster, that has to be done slightly differently, which we can, I don't know if we have the time, I'll just briefly tell you about that and we can see that. So the first assignment which we have for today is, this is the same list which was given to you all yesterday, for which you all created catalogs, right? So your homework was yesterday, you had to do it at least for one cluster, create a catalog like we did yesterday, like you did that for 5466 yesterday. Do it for any of these globular clusters, find out the catalogs with two bands, G band and R band, using SDSS data, and then use that data to actually get the distance to these globular clusters, right? And if you remember yesterday in the end of our session, we also did HST data, right? And HST data can be used to, again, download the image, get the catalog, plot the HR diagram, and again, get your parameters exactly in the same way like we did it for SDSS. The only difference being is you'll have to change your 0 point in the APT tool, right, which I showed you yesterday. You'll have to change this thing. So I'll just now pause over here. I'll take some questions and then I'll proceed. So please let me know if you have any questions about what we did till now. Is this clear or do we move ahead? So Ishan, thank you for the question. How did you get the 0.6 magnitude value? So this is a value which is actually a given. We have this value. If you actually search online, you'll get absolute magnitude. If you write absolute magnitude of horizontal branch stars, right? You will actually get the plot itself I showed you, where you can see there are papers on this, on the absolute magnitude of the red horizontal branch stars. So for example, in this paper also, you have a thing which says what is the value, right? So in short, this is stuff which you actually get from the we wanted it the same. That was for UG. Okay. That was for UGRIZ. This is exactly the Sloan Digital Sky Survey. Those are these things. And therefore, you can see that this. So we can actually have a look at this paper. And this is exactly for Sloan data. So for Sloan data, which is UGRIZ filters, it's actually telling you what are the absolute magnitudes. So let us look at this. And this is for different metallicities. Here is this thing, right? So what they did is that they used observations of various these things. Here you can see. But this is the red horizontal branch. This is the right part, not this. We are looking at the blue horizontal branch. And they get the magnitudes, right? So this is basically a given. We take it from data. So here you can see, this is mg. Yeah, you can see over here, for Palomar 3, it's 0.6, 0.6, 0.64. These are the values which they've got for different clusters, right? So that's how we get those values, right? Okay. Oh, sorry, you could not see my screen. I'm sorry. 1 second, I'm sorry. I will... I'm sorry, I'll show you this thing. So it started off something like this. I searched absolute magnitude of horizontal branch stars, okay? So these are published data which people have actually been working on and giving. So if you actually search for this, let us search for absolute magnitude horizontal branch stars. You can see this first hit itself is absolute. Hasan sir, So here you can see that this is a paper which has absolute magnitude horizontal branch. If I click over here, the PDF, you can see over here where, um, you know, here are the values. So you can see this is for G magnitude. Yeah, look at this table over here. There is G magnitude. And for Palomar 3, it is 0.6. For this other globular, it's 0.6. For M3, it's 0.64. So these people determine the values for a bunch of these things, right? So approximately 0.6 is an approximately fine value. You can take it, right? So that's fine. I'm sorry about the screen problem. Yeah. If any more questions, please ask them. So essentially, we have not spoken about how to get masses and stuff like that, but trust me that you can find out all parameters of those stars in the globular cluster because you have plotted the HR diagram and you have the distance to the globular cluster. So we can do that. Yeah. So please ask your questions. I'm waiting.
Why we have specifically chosen the horizontal branch of globular cluster? Is there any other reason?
So I'll just give you 2 minutes. Just give me 2 minutes. I'll just be here, and please write your questions in the chat window, right? So, are there any questions, or should I continue? Should I continue? Are there any questions, or should I continue? I think I'll continue. And yeah, I can't hear you. Hello, is somebody trying to ask a question?
Yes, ma'am. Yeah, just. Hello, ma'am.
There's a lot of background coming, Surinder. There's a lot of background coming. You want to ask a question? Yeah, okay, I'll just continue.
Can you hear me now? Sorry.
Yeah, I can hear you.
Yeah, madam, is the what specifically chosen this horizontal?
Now again, I can't hear you.
Sorry. Now.
Yeah. You want to ask a question, Surinder? Surinder, do you want to ask a question? Surinder, if you want to ask, okay, okay. Yeah. Your audio is very bad. There's a lot of disturbance coming. There's lots of static. Okay. So I can see your question. You have given me a question. Why specifically horizontal branch stars? So horizontal branch stars are useful ones because they fall within a very small magnitude range. So that is a good way of doing it, right? That's not the only way of doing it. There are many other ways also of studying star clusters, which I will now start, which I will continue talking about. But with globulars, it's very important and very good to use horizontal branch stars. Similarly, other stars can also be used, which, for example, I'll show you again. If we look at the right, so if we so over here, you can see that this is a globular cluster, right? So in the globular cluster, what happens is you don't have many stars on the main sequence, okay? Generally, for other clusters, for other things, we use the main sequence to actually calibrate and get the distance to, to the cluster. But in a globular cluster, since most of the stars have evolved, right? That's why they are all sitting over here in this giant region, right? And the problem with the giant stars, the stars of this region, is these are often variable stars. Okay, so their brightness varies a lot. Okay, so you cannot use these stars to calibrate and get distances to globular clusters, because these stars often are variable stars, and they are problematic. The horizontal branch stars are the most important stars in globular clusters, because what happens is the horizontal branch stars, they occupy this area. So you can see that they are classified into all these types. There is the this one, you have this, the red giant branch. The RGB is the red giant branch. The green stars you can see over here are called RR Lyrae stars. Now, RR Lyrae stars also you can see here have a very small range of brightness, right? And therefore, if I can correctly identify RR Lyrae star, supposing I am looking at a globular cluster and I can identify an RR Lyrae star, I know from the beginning what is the absolute magnitude of this RR Lyrae star. And therefore, when I observe it, I see the apparent magnitude and I can immediately derive the distance to that globular cluster because of the RR Lyrae. So people study RR Lyrae stars basically because of that. Then the yellow stars over here, which we have, are what we call the horizontal branch stars, which we were talking about today. Then there is these blue stars. These are called the asymptotic giant branch. So the giant branch is the red, but on top of that is called these blue stars, which are called the asymptotic giant branch. They're on top of the giant branch. And these brown ones are the regular stars. So when we study globular clusters, since these giants are not that useful because of the variability, we typically use these stars. Either we use horizontal branch stars or we use RR Lyrae stars, because again they have a smaller range of brightness and you have to take it from here, right? So that's why we have to do this for that. I will now talk to you about open clusters. See, if you look, remember this plot which I showed you, I'll show you this. Here you can see this is an HR diagram not of an open cluster. That open clusters are generally younger, and many of the stars are there on the main sequence. A globular cluster looks like this, where most of the stars have gone away from the main sequence, so I cannot use the main sequence to actually calibrate it or find anything. So that is why we use these horizontal branch stars. But if we use younger clusters where there are more stars on the main sequence, then in that case, we use what are called isochrones. And that's what I'm going to talk to you about now a little bit. And isochrones are basically lines which have the same age, of stars which have the same age. And they are what we then use to get this thing, right? But I would like to stop the share and like to tell you that, see, in this thing, we basically spoke about SDSS data, we spoke about HST data, but along with this, there are many other data sources. If there are any data sources for which you have magnitudes of stars in two filters, right? In two filters, then you can always use that to plot an HR diagram, right? So if you actually look on the net, right? I will show you on the internet, right? Right? You can actually find a lot of, for example, there are many data sources. For example, if you look at some star catalogs, right? Right? If you have any star catalogs or star cluster catalogs, right? Specifically for star clusters, right? You can actually find a lot of data for stars. Let me, for example, show you. If you want to study in the infrared, right? You can look at what is called the 2MASS database. The 2MASS database is a database which has brightness of stars in infrared bands. Okay, and this is the JHK bands. Okay, J band is 1.2 micrometers, H band is 1.66 micrometers, and K band is 2.159 micrometers. So what TUMAS has is it has catalogs for the whole sky, right? And therefore, see, one step was what we did yesterday was where you get images. So you took images to create catalogs, right? The other option is you directly access catalogs. Okay, so if you access catalogs, you will already know the brightness of the star in say 1, 2, or 3 wavelengths, right? And you can use that directly to again plot it and get an HR diagram. So for example, now here if I do catalog search, let me go to catalog search of 2 micron. And you see over here, this is called the 2MAS All Sky Point Source Catalog. So that's what we are going to select. We are going to look at the point source catalog. The 2MAS also has extended sources. So extended sources basically means galaxies. And then there are some others. So let's just take the point source catalog. I'll say select. This is the point source catalog. So if I want the same very cluster I looked at, NGC 5466, right? I can actually get the data for NGC for this thing. I'm going to increase the size because it's only 10 arc seconds. I'm going to make it 10 arc minutes, right? A larger size. And I can actually ask for the data. So what happens is the table output. If I want, I can give an email. I can say, put it in an email, or I can just just run the query. So I'm running the query, right? I'm looking for NGC 5466, and this is now showing me what are the sources. So in NGC 5466, it found 420 sources, right, within this area. This is the same cluster we were looking at yesterday, right? This is exactly the same cluster, okay? And this is now giving me the data of this in infrared, right? So I can look at the data over here, which you can see over here. And here again, we have, this is the array, this is the deck. This is if you look over here, this is the J magnitude, this is the H magnitude, and this is the K magnitude, right? So you can directly, what we did yesterday, you can jump that step. You don't need to make a catalog. You can already use available catalogs and actually get it. So if you want, you can click on full result table. This is the table, right, which is here. You can see it over here. I can save this thing. I can save as, okay, as a text file. So I'm going to save this as a text file in our Day3, okay? And I'm going to write NGC 5466, and this is from TUMAS, right? So what does it have? It has JHK data. So I can say save, right? And now if I want to look at this data, what I can do is I can again open my good old Topcat, right? And with Topcat, I can again say file, I'll say load table, and I'll say file browser. And okay, this is looking for CSVs. I'm going to tell it to look for auto all. Oh, you see, otherwise it's looking only for text files. Now because I've told it that it can take this. Where is that file gone? Oh, sorry, we are Day3. I'm sorry. We are in Day3. I was looking in Day2. So this is the file which we want, and I take it. The problem with this file, if you remember, is it has all this stuff in the beginning, right? And therefore, what I'm going to do is I am going to clean the file. So the file that you have downloaded, right? We are going to clean it, and the other option is you look at the file and find the line from which the text starts, right? So this is the thing, right? And I can remove all these comments which are there in the beginning, because otherwise it can't open it. I'll delete this all. Remember, we had a similar problem yesterday also, because there is header information in a table, right? So I'm going to say save. And once again, I will try opening it from TopCat. So let me go back to TopCat. I'm going to say file, I'll say load table, I'll say browser, I'll say this. So now you can see I've opened the
Madam,
file.
your screen.
You can't see the screen? Okay. Okay. I'll say stop share. I'll again share, I'll reshare it again. So I opened my TopCat, right? And in TopCat, I say file, I say load table, and now I'll try to open this text file. This is the text file which we just downloaded, which is NGC 5466 2 mass JHK text. I say okay, and here you can see, here is my file. So we have lost the headers, but here you have the RA, here you have the deck, and here I have my, you have, you can see column 7 is J, column 10 is H. So I can, let me rename it. Let me call column 7 J, and column 10 is H band, and column, this is probably K. I'm not too sure whether that is that or that. Okay. So now what I can do is I can now make another HR diagram. I'm going to show you a different HR diagram. Again, I'll click on this, and this is our globular cluster, right, which is with RA decks. But now let me plot the HR diagram. So the HR diagram I can say is J minus H, right? I'm going to take the difference, shorter wavelength by versus longer wavelength, and this. So, oh no, I think that was not that was not the this thing. Maybe I've made a mistake. So I will replace this column as, oh, I don't want this. I think we made a mistake. Maybe this is J. We made a mistake, H and K. I will take H minus K. Oh God. No, I'm sorry. Let us, I've made a mistake. I need to find the correct columns. So let us just, I misidentified. So this is RA and this is deck. Let us now see what I think is J, H and K. Okay, maybe this is not it. So this could be K band. This could be H. Okay, this one is no. So we say, I'll say no, this is not it. I think this is must be the correct one. This one is H. I'm sorry, I wrongly identified the column because I deleted all that information, right? So I've lost it. So let me go back to this here. Let me do this, and I will make it H minus K versus K. Yeah. So now here, this is the HR diagram we have created using JHK data, right? Now the problem in this case, you can't see it very well because it's a very old cluster, and therefore in infrared, these stars are not going to emit too much of emission, right? So we actually do not get, yeah, our HR diagram does not come out so well. But similarly, what you can do is you can actually look for different data sources to actually get more data. I am not going to get the time to talk about this today, but the most recent sources of photometry in today's times, I hope you can see, is we will not talk about it, but I wanted to just mention to you that there's a satellite called Gaia, okay? And Gaia is basically a satellite of the European Space Agency, okay? And basically what it does is that it observes stars, okay, using two telescopes, and it has those two identical mirrors. And with that, it actually gets you a lot of data for stars in our galaxy. So, a billion stars of our galaxy, we have data using Gaia. So, for these stars, billion stars, we have their RA, we have their deck, we have what is called parallax. Okay, so parallax is a measure of distance. So 1 upon parallax is the distance to a star. Okay, we also measure the radial velocity of these stars, right, by doing spectroscopy. And we also measure the motion in the plane of the sky, which is called proper motion in RA and proper motion in deck. So basically, what Gaia gives us is it gives us a 6-dimensional image of the stars of our galaxy. So for all the stars in our galaxy, a billion stars, it tells us their exact positions, their exact distance, their exact motions, right? And so therefore, the most perfect, since we were talking about HR diagrams, I could not resist this, but I had to tell you about this, that the most precise HR diagrams today are the ones which we have with Gaia. Okay, so Gaia data is actually used to get these HR diagrams.
I think we should explore.
So what I'll just show you is how they actually constructed the HR diagram with Gaia data. So you have very perfect clusters observed, for which you know very well which ones are members, which ones are at the right distance, right? And then while they look at these stars, they can actually get the photometry, the brightness of these stars, right? Because we are, see over here, like I told you, we have a 6-dimensional image. We know the distances to stars, we know their motions in the plane of sky, perpendicular to the plane of sky, we know exactly how they are moving. Now we sort the stars in terms of their brightness. And if we sort them in terms of the brightness, this is the HR diagram. The brighter stars are, luminous stars are on top, the less bright stars are down, hotter stars are the left, and the colder stars are to the right. So since we have all this perfect information from the data of Gaia, we can actually make such a perfect HR diagram for the stars with the Gaia sample, right? Um, so that was the earlier data release of Gaia, which was called the Data Release 2. So with Data Release 2, they got this is an HR diagram for all the stars. So you can see now this is like overlap of many clusters and many field stars, stars which even do not belong to clusters. So therefore you can see here you have a main sequence, you have a giant branch, and you have what? White dwarfs. So like I mentioned in this, you have, it's like an addition of all the stars in our neighborhood, all the clusters and all the field stars also, the stars which do not belong. This was the data release 2. Last year there was another data release which is called the early data release 3, which gave us even more accurate data. And using this data, they got even a more perfect HR diagram. So in today's time, the most perfect HR diagram is the one which we have with Gaia, which is from the early data release 3. So I'm again going to just show you how they generated that, exactly like how they generated the one for DR2. We look at stars, we get their distances. From their distances, we can calculate their exact luminosities. We know their temperatures because we know their position on the HR diagram. So this is from the sun, we are going outwards, away from the sun, right? And as you go away from the sun outwards, you can see there are a whole set of stars, which you can see as you go outwards. And we are, going out of the solar system. This is the solar neighborhood, the stars in our solar neighborhood. But because of Gaia, we know the distances to these stars. And once we know their distances, you see this is stars which are within 400 light years of the sun. If we look at them, we know all their distances and all their velocities. And hence we can convert them all to absolute luminosity and absolute temperature. And we can plot them all on the HR diagram. So first of all, we sort them by luminosity. You can clearly see in this, this is a very interesting plot. You can see that nature produces very few high luminosity stars. The bulk of stars that nature produces are low luminosity. So you have more stars on top, less stars on top, more down. There are more low luminosity stars than high luminosity stars. And then we sort them by color. And after we sort them by color, we get this. And this is amongst the most perfect HR diagrams we have in today's times, which we have derived using Gaia data. So I would like to conclude with this because, like I mentioned, this is the best source of, the best HR diagram which we have today, thanks to the Gaia satellite. So you can also Google and look for Gaia data, and again look at the same sample of stars using Gaia data, right? But today we don't have time to go into more detail about Gaia data, in the sense, how do we handle the parallax and how do we handle, the radial velocities and the proper motion. We can't cover that today. But in principle, the best HR diagrams one can get in today's times would be the ones which you would get from Gaia, right? So I'll wind up with this, and we'll stop with this, right? There are some basics, if I can go through that if we have time. But before that, I'd like to stop and check if you have any questions. So first, let's check if you all have any more questions. And that will end our deal on the HR diagram, right? So are there any questions? Or yeah, are there any questions? So if you don't have any questions, I'm going to proceed, right? I just thought that for people who are not from an astronomy background, I just wanted to add a little bit about some astronomy basics, right? In case you do not know them. So I'm just going to cover a little bit of these basics. I kept this just for the last 15 minutes because in case there is time. And now since there is time and I don't see any questions, I will just proceed a little bit with these basics. They may be helpful to you. So let us see, what do we actually observe in stars? When we look at stars, what do we actually observe? The first thing I think I spoke to you about was parallax. That is, parallax is the way we measure distances, right? So we have two eyes. Our bifocal vision helps us to perceive depth. And how do we do that? Because both the eyes look at the same object, subtend a certain angle, and that gives us an idea of distance. So you know that if you close an eye, if I were to close my eye and now were to estimate distance, it's very difficult for me to estimate distance. For distance, I need both my eyes open so that I can measure parallax, right? But what we do it in astronomy is the distance now is my baseline, which is the distance between both my eyes. If I want to measure angles more accurately, I want to increase the baseline. How can I increase the baseline? Is we know that the Earth is going around the sun. So if I look at a particular star today and then I look at the same star after 6 months, I will get this bigger angle, which is the parallax angle, and I can measure distance. So my distance is just going to be 1 upon the parallax angle, okay? Because that's how it's defined, and that will be the distance in parsecs. So the distance in parsecs is the distance at which you will subtend an angle of exactly 1 arc second. And that's why a parsec is so called, right? Because it is a distance at which you will subtend an arc second if your baseline is defined by the astronomical unit, 2 astronomical units, which is the distance of the Earth from the sun, which is 150 million kilometers, right? So I think I spoke, so in Gaia data, you will see parallax, and parallax is the important thing because it's going to give you the distance, right? So what we did with horizontal branch stars, you do not need to do that. You can just directly, if you know the parallax of the stars, you can find out its distance. So there's a video showing you what is parallax. So if I were to look at something from 2 angles, right, I can actually estimate distance, right? That's what I do if I look from 2 eyes, right? So parallax, like I mentioned, is 1 upon distance, and the distance, if you do distance is 1 upon parallax, that will give you the distance in parsecs, right? So parallax measurements, if you want to measure the distance to stars, how do we measure the parallax? Using the method I showed you, the closest star to us, Proxima Centauri, has a parallax of 0.7 seconds, right? Bernard star, which is another star which is reasonably close to us, has a parallax of 0.54 seconds. And when we measure errors in parallax, it's about 1,000th of an arc second. And therefore, with the earlier satellite, which was called Hipparchus, we measured parallaxes to the extent of 1,000 arcsecond. Right. So this was a satellite which was sent many years back, which actually accurately measured the distance to 1,000,000 stars. Now with Gaia, we are actually doing parallax accuracies of a micro arc seconds, which is 10 power minus 6 arc seconds. And therefore, what you can see is that with Gaia, we are getting much more precise parallax or distance estimates to stars. Why do we want the distance? Because we want to get the luminosity. How do I have the luminosity of this thing? If you have the sun, for example, it's giving out certain amount of flux, right? The flux is sigma t power 4. And then depending upon the area, you will have luminosity. So flux into area will give you the luminosity, right? And luminosity does not depend upon distance, right? This is the distance, the luminosity. It only depends on the solid angle. So you cut the solid angle at whichever point and you will get the same. Flux depends upon solid this thing, because flux will change. It is, you see, this is the flux over here, this is the flux over here, and here is the flux at a different distance. So the flux goes as 1 by r squared, but the luminosity will be constant. So for example, for the sun, we say the sun, the luminosity is 3.8 into 10 power 26 watts, right? That is for the sun. But the flux will vary depending upon the distance. So for example, Mercury gets maximum flux because it's closest to the sun. Pluto gets minimum flux because it's further away from the sun, right? So luminosity, like I said, it's given by sigma t power 4. Area is 4 pi r squared. Total luminosity is 4 pi r squared into sigma 2 power 4. So obviously for that we need to know r. This is the distance to the star and the temperature, which we will get both of them from the HR diagram. So if you had two stars which have a flux of A versus B, it would be basically the ratio of the luminosity and the inverse ratio of their distances, because flux goes as 1 by r squared. Right? So Hipparchus, he was the first one to actually measure the brightness of stars, and he set up this thing which is called the magnitude scale. Right? We spoke about magnitudes, and this is the magnitude scale. So the magnitude scale is like the sun, absolute magnitude is minus 26, the full moon is minus 12. But if you look at, for example, Sirius, it is minus 1.5. Betelgeuse in Orion is 0.8. And you see, if you had a 1 meter telescope, you would probably be able to observe till about 16, 17th magnitude. If you have a 27, if you have the Hale telescope, it gives you approximately 27, and then Hubble and Keck give you about 30th magnitude. So the magnitude scale, like I told you, it basically is an inverse scale. The brighter stars have negative magnitudes, while the fainter stars have larger numbers of magnitudes. It's a logarithmic scale. And we can actually convert it to magnitude scales. So this is how you do magnitude scales in astronomy, where this is the difference. Like, so this is what I just mentioned. The sun is very bright. The brightness is minus 27. The moon is minus 13. And when we look for fainter objects, we often look for objects which have a brightness of 25, 20. If you remember what we were doing today, we were actually seeing the faintest objects, which are a magnitude of about 20th magnitude, right? That's what we were getting with SDSS. If you were looking with Hubble, you'll go fainter. Absolute magnitude, we spoke a little bit about it, was that you scale all stars to the same distance of 10 parsecs, and that's what you do to find out its absolute magnitude. And we find out what is called the distance modulus for stars to get their absolute and apparent magnitudes. So this, I've already showed this thing to you. Bolometric magnitude is you measure the magnitude in different wavelengths and you add them all up together to get the bolometric, the complete one. And we did this yesterday, which was photometry, measuring photons, and how do we do the photons. So I will just stop with this. I just thought that these were some basics which we needed to cover. I think we've done it today, the UBV system and the temperature part. Right? So I'll stop with this, and I'll again take a little questions if you all have any questions. I just added that basic stuff because I thought there could be possible some of you all who do not know those things. They would take a lot of lectures, so we don't have time for that, but just to give you a basic thing. Are there any questions? Would you want to ask any questions? Are there any questions or should we stop now? I can stop. I think you all are tired. Right, you all seem to be tired. So we'll stop with this and I'll see you all tomorrow. Tomorrow we are going to work on another scale. So we did exoplanets, we did star clusters, catalogs, we did HR. Tomorrow we are moving to another big thing. We are moving to dark matter and gravitational lensing. So tomorrow I will talk to you about dark matter and gravitational lensing and how can we actually estimate dark matter using real data, right? So we will actually be using real data with which we can actually find out the amount of dark matter, right, in some galaxies. So we'll do that. Okay. Thank you so much, Wabi, for your appreciation. Thank you so much. Thanks a lot. But I look forward to seeing you all tomorrow. Let's meet tomorrow. Do try doing some of that assignment or the homework and see how easy or difficult is it for you to do. And while we are meeting, you can ask me questions if you all have any doubts, right? So thank you very much and we'll meet tomorrow at the same time. Yeah. See you. Bye-bye.
Yes, Priya, are you done with the meeting? I'll stop.